So many chairs. No. Okay. Number 29 says expected value for life insurance. This is what I was talking about the other day about how they use those P of X tables to actually set premiums for all kinds of life insurance and car insurance and all this kind of stuff. This is why when you turn 25, your car insurance only goes down. You wake up and you know how to drive. I see some people just never wake up. 0.9986 probability that a randomly selected 30-year-old male lives through the year. So probability live. What was it? 9986. Okay. At least that's very high. That's good. Fidelity Life Insurance Company charges $161 for ensuring that the male will live. If the male does not survive the year, the policy pays out $100,000. If he dies, pay out $100,000. From the perspective of the 30-year-old male, what are the values corresponding to the two events? And I would argue from the perspective of his beneficiary, if you read through this whole thing, but let's just go with what they say. What are the values corresponding to the two events of surviving the year and not surviving? I love it. So, what are the values corresponding to the event? Yeah, so what they're really asking is when you start to put this table together, these are the values of the variable. So what are the values that I would put in there? What two things could happen? This dude could live or he could die, right? So you can actually put in English over here, live, die. So if he lives, what's the monetary value there? Is he losing money? Is he gaining money?
Minus 161.
Yeah, good. He's got to pay $161, right? And this is why I'm talking about his beneficiary. If he dies, he ain't getting shit. His value would be zero, I'd argue, right? So let's talk about his beneficiary, his family, whatever. What's the value then if he dies? Was it 100,000 or 10,000? 100,000. Now be careful. Bless you.
Thank you.
It's not 100,000 really. It's 100,000 minus 161, right? So it'll be like 999,839,839. There it is, Jeff. Is that cool? You guys with me? Let me just stop right there for a second. If he lives, he's out $161. But he's got to pay that premium no matter what. So he pays a premium and then he dies. So he gets $100,000, but he had to pay that $161 for his insurance to continue anyway. So he's out that too there. But he's up $998,839. You guys semi with me so far? That's just putting down what's going on here. So if you win $1,000 from a lottery ticket you purchased, was that your profit? No. Your profit was minus $1, however much that ticket cost. Your actual profit was $900. So his profit here would be this much because he had to pay $161. Yeah.
I did minus the 161 to the 100,000, and I got 99.
Oh, I mean, one too many.
Yeah.
Nice, thank you. I was giving him a larger deal. Exactly. Thank you. Now, what are the probabilities associated with both of those? What's the probability for right here? What happens? What's the probability this is going to happen? Yeah, 0.9986. And what's probably this is going to happen?
0014.
Yeah, the rest, 0014. Cool. And now you just attack it like you do any of these other problems. The reason this one's harder is because they don't give you the table set up already. You have to set it up yourself based on the situation. But you just put in, you can write in English what would happen, then you write the values associated with both of those cases, and then you figure out the probabilities based on what they told you. And now you can just attack it, XP of X, figure out the expected value. You guys kind of with me? Now, from the 30-year-old male's perspective, his expected value should probably be positive or negative. Should be negative because from the insurance company's perspective, they're going to set things up so that their expected value is positive. They want to make money. Right? So now you just got to plug this in the old calculator, figure out x, p of x, and then sum that bad boy up for the expected value. There's some other problems in there, like there's the lottery problem. That's just like I just said. It's basically exactly like this. Either you win or you lose. You have to pay so much money to play, so forth, right? Okay, maybe. Again, no, I want to play poker with you people. Anyway, keep my ass. All right. Now I'm really curious as it comes out, but I'll just wait and see. It says, the last question says, can the insurance company expect to make a profit if his expected value is negative? It's negative because money's flowing away from him, and of course it's flowing to the insurance company. Yes, ma'am.
Where did the subsidy go? 14.
14? Any other questions on that guy? No. We'll call him John. And he dies at the end. So number 14. Ever seen that movie, John Dies at the End? Okay, no. It's freaky ass movie. Range rule of thumb. Okay, use the range rule of thumb to identify a range of values containing a usual number of p's. Blah, blah, blah. So saying, what's the usual number of p's with this one here? The one about the peas with green pods? Yeah? Let's see, refer to this table. Cool. And when you're doing this, how do you figure out the range of usual values? What do you need to have before you can figure that out? How do you figure out the min and the max? Yeah, you need the mean and the standard deviation. And then you can, how far do you have to go to get the usual range? Up and down by how many standard deviations? 2. Cool. I love it. All right. And why does that make sense? Because what's the empirical rule say about within 2 standard deviations? How much information? Careful, that's chubby dude. Yeah, empirical rule says, still chubby dude. 95% within 2, right? 68, 95, 99.7. So if there's 95% in between, within 2, how much is outside of there? 5%. So it would be freaking unusual to be outside of there, wouldn't it? So it makes sense to set it up as between 2 and negative 2 standard deviations away from the mean. That's usual. Because outside of there's only 5% chance of that. That would be unusual. Maybe. So in this problem, you take the table they gave you, 0 and the p of x and blah, blah, blah. You do your, you get your mean, and you get your standard deviation. And you got to use a formula for that. And then you figure out your maximum and your minimum by doing the mean minus 2 standard deviations, the mean plus 2 standard deviations. So if you start at the middle, and you go up a couple of average distances from the mean, you go down a couple of average distances from the mean, the empirical rule makes sense. You should catch a lot of your data, since 1 standard deviation is the average distance away. So if I go 2 steps away, I should catch a big chunk of my data. Because I've just gone twice as far away as most data is on average. So I should catch a lot of my data. And then it says, is it unusual to get only 1 p with a green pod? Well, then you just see if 1 is in your usual range or not. No. So if your usual range is 1.5 to 3.5, then 1 would be unusual. Is that cool? Let that part be easy. That's kind of nice, actually. Don't let that part freak you out. Let that be the easy part, because that's not the hard part. Any other questions from chapter 5? Yeah.
26A.
Oh, the New Jersey lottery? Yeah. every time you go on the turnpike there, you're playing some kind of a lottery. Have you ever been up there? No? You should go. Paramus is nice. 26A. Oh yeah, I agree with you. So this one's about, you can pick 4 digits. And I'm going to help you out. They're a little bit reticent to really let you know what's really going on here. You could pick, using 0 through 9, how many 4-digit numbers can you come up with? So that sounds a little freaky, but it's not. What's the smallest 4-digit number you can come up with? And it sounds weird, but you actually could have 0, 0, 0, 0. Right? Up through, what's the highest one? 9, 9, 9. Well, how many numbers is that? I like that.
10,000.
10,000, right? Why is that? Because 0 through 9 is how many digits? How many numbers? 10. So 0 through 99 is 100. All right, keep going. And then you get up to here, then how many is this? This will be 10,000 numbers. What's another way to do this? I want 4 digits. How many digits do I have to choose for this one? 10. And this one.
10.
And this one, and this one. If you multiply that out, you get 10,000, the same thing to get the other way. How's that? Is that cool? And that, of course, is crucial because that, if you can't get part A, you can't set up your probabilities for the rest of the problem. You're right. So if any of you guys started at 1,000, I understand. Because you're like 978, that's not a 4-digit number, but it would be if you put a 0 in the front of it, right? Okay, so if you start at 1,000, I don't blame you. You don't have to go back and redo the problem, but officially it should start at 0, 0, 0, 0. So what's the probability you win if you play one number? What's the probability you win?
Out of this, 1 in 10,000.
1 out of 10,000, because there's one winning number out of 10,000 possible numbers. So it's a 1 out of 10,000 chance, which is a hell of a lot better than most lotteries, right? Okay. Which the only way you definitely can't win is if you don't play. But just don't play, man. College kids, you do not need to have something else taking your money away. Right? Okay. Anything else from chapter 5? I should say college students. Some of you guys are not that much younger than me. Okay, so today we're going to do a little bit of a review of binomial, and at the same time we'll be sort of stepping into chapter 6, which is the most important chapter in the book. All right, so as you look at this, some freaky stuff on there. Let me point out one thing. Actually, let's just go straight through this. Let's do this review here. At the very top, go ahead and do those first 2 prompts. This is a little review of what we did the last couple times. If you weren't here last time, you might not be able to do too much with that. Problems up here. All right, so help me out. What's n here? 14, cool. I'm flipping that thing 14 times. What's p? 0.5, so what's q? 0.5, cool. Now in this specific case, the formula can simplify a bit since p and q are both the same, but we're just going to attack it direct without realizing that. So it's probably exactly 9 heads. So what would 9 be? What variable would that go in for? X, cool, because X is my number of successes. I want 9 heads, I want 9 successes. So I have, how do I set this formula up then?
14.
Good, so 14, choose 9. So how many of these do I have? 9, and how many of these do I have to have then? 5. Cool, so some of you guys I know understand that, but just put those together. Any question here would actually just have 0.5 to the 14th at the end. Well, we'll just attack it like we don't realize that. And what do you guys get for that?
Like 1, 2, 2, 1, 9.
1, 2, 2,
1, 9.
1, 9. So we'll just have to 1, 2. I'm trying to let the computer warm up so I can remind you guys how to do that in your calculator. How do you set up this one while we do that? What would at least 2 heads be? Now be careful. You're starting to set up exactly 2 heads. This is at least 2 heads. So if you wanted to do at least 2 heads directly, what would at least 2 heads mean? You can get 2 heads or more, I like that, or 3 or 4. So if you want to do this directly, you have to do probably 2 plus probably 3 plus all the way up to 14. Okay, so thankfully I agree with you as you say in your head, screw that. It's a bit too much work to worry about. So I'd much rather, you can always do the opposite probability and subtract from 1. You especially want to do that when the opposite probability is less work. Does that make sense? So you can always do the opposite probability and subtract from 1 anytime you want to. Here I really, really want to. What's the opposite of at least 2? 0 and 1. So now I just have to get the probability of 0, get the probability of 1, add them, subtract from 1. Is that horrible? No. So then we can set this up, 14, choose 0, 0.5 to the 0, 0.5 to the 14. And 14, choose 1, 0.5 to the first, 0.5 to the 13th. Is that cool? 1 minus 0 or 1. So as I say it in English, you can actually see how it's set up in that equation. Let me show you how to put that in your calculator. This one will come up. You guys all got that right? I'm back to the computer. Yay. Here we go. Good. So to put this in, I'll do 1 minus, parenthesis, 14, choose 0, 0.5 to the 0, minus 0.5 to the 14th. Now some of you guys might realize I could have just put in 0.5 to the 14th for that, because the other 2 pieces of that are, let me do this for you. The other 2 pieces to this are 1. 14 choose 0 is 1, 0.5 to the 0 is 1, but I'm just going like I don't know that. Plus, now notice I put this parenthesis in there, right? Because 1 minus the sum of these 2, plus 14, choose 1. This is for the probability of one head times 0.5 to the first times 0.5 to the 13th. I'm really putting more in than I need to, but just so I can see the whole formula up there. And so I get 0.9991 basically. Is that cool? You guys see that? So the one we just did, the exactly 9 heads, who remembers the shortcut to get that? Because if you do that 14, choose, you do Jeff 9, 0.5 to the 9th, 0.5 to the 5th. So that's where we got the 0.1222 thing earlier. What was the shortcut? How do I get to the shortcut? Good. You go to second, right above vars to DISTR for distributions. Go to binomial. Which one? Which binomial? C or P? P, because I want a particular value. I want exactly 9. And what are the inputs for this? What does it need to know? N, comma,
Q.
P, and X. I love it. It doesn't even know Q because it can figure out Q on its own. It better be able to. It costs enough money. So thank God we get exactly the same number. Whew. All right, cool. Yes, ma'am.
How would you use that for the cumulative one?
Oh, if you want to do, for example, the other one, too many options. There we go. If you want to do the probability of at least 2 heads, it was 1 minus 0 or 1, right? So I could do binomial CDF 1, and it would go 0 to 1. Remember, binomial CDF, it always goes up to the number you put in. So if I did binomial CDF, blah, 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 9. If I did CDF there instead of PDF, it would add up 0, 1, 2, all the way up to 9. So to get part B, or number 2, sorry, to get number 2, I could do 1 minus binomial CDF, and then N, P, and then I want to go up to 1. So what that right there, the binomial CDF, blah, blah, 1, that's going to add up 0 up to 1. So hopefully it's going to come out to be 0.9991, thank God. Is that cool? Obviously really useful if I'm saying you have 1,000 people and I want the probability of, at most, 200 of them. I'd rather do binomial CDF up to 200 than do the freaking formula 200 times. Okay. Do you have to know how to do this? No, you don't have to know how to do this. That's not part of the course. But if you want to know how to check yourself, you figure out how to do this. Oh, there you go, Jeff. Around we go. Hey, computer. Okay. Now, real quick. So now you have this whole little piece is all about what we just did. How to do in the calculator, the binomial PDF part at least. What would the mean be? If I flip a coin 14 times and I get half of them are heads, the mean, of course, would have to be 7. Now here's the part that I can't really answer as easily. The variance would be 14 times 0.5 times 0.5 NPQ. Somebody help me out there. Well, that's pretty easy, right? Half of 14 is 7, and half of that is 3.5. So what's the standard deviation then?
1.871.
Good, the square root of 3.5, which is 1.871. 871, thank you. So we got our mean, and we got our standard deviation. Coolness. And that's from that last section we did, that section 5.4. The 2 most beautiful little formulas for mean and standard deviation yet. Now here's the thing. Look on page 603 in your book. I haven't really talked about this yet. I'm not really going to talk about it much because hopefully you understand this is not the most useful thing in the world. So what they've done here is, in very specific cases for probabilities of success, up to only n equals 15, they've kind of written out all the possible probabilities. If I have 14 flips of the coin, how many heads could I get? None up to 14. So if I go 14 and I scroll over to 0.5 probability of success, here's all my probabilities for everything. And here's 9. There's the 0.122 we got earlier. Here's 0 and 1, and if I add those together, I get basically 0.001. What does 0 plus mean again?
Under 0.05?
Yeah, under 0.005. Right, so it could be at most 0.004. Yeah, actually not even that, under 0.0005. So that's pretty damn small. So if I do 1 minus this, I get that 0.999 we got earlier for that problem. How are we doing there? Now, if you look at this should hopefully look sort of like a frequency table. In fact, this is a relative frequency table. Here's my values, and here's my percentage of the time I get those values. Does this look normal? Does it start low, go high, and go low again? Yeah, and in fact, this is even more than just casually normal, which is a very strange phrase, but there it is. I love that, casually normal. It goes high and it goes low. And as it goes up and it comes down, it's exactly symmetric. So that's what I put on the paper here, is something a little more visual for us. It's this part of the table in histogram form. Well, that's exciting. But this is the reason I want to do this, is because histograms we know. We sort of know the binomial probability distribution. I mean, we're still kind of getting it, but it's there. If I were to ask you questions like the probability of at most 6 heads, at most 6 would mean what? It would mean it could start where and go where? At most 6. You could be at most 6. 0 up to 6. Good. So if I want to know the probability of most 6 heads, how do I get it from my picture? Add what? 0 to 6, I love it. It's that simple, right? Probably most 6 heads is 0 or 1 or 2, and of course or means add. Right? So just add all these up. So somebody help me out. Add up all the way up to 6. What do you get for that? So 6 is 0.183. 305. 366, 388, 394, 395? Is that right? Yeah. All right. Good job, Matt boy. Okay. How are we doing so far? That's pretty simple. Why was that such a simple thing to do, really? I mean, and do you see how visually I can see how the probability relates to the area? How wide is any of these rectangles? How wide is that, do you think? What does that go from to? 5.5? 6.5. So how wide is it? 1. So it's the area of this rectangle. 1 times 0.183. So isn't the area of this rectangle equal to the probability of what it represents? So if I can put a probability distribution and give it to myself visually, right? I can find any probability I want to by just getting the area. If I want from 2 to 7, I just get the area between those two, and that's the probability. That seems awesome, right? Especially when my image is an easy shape. If I had a distribution that was exactly triangular, then maybe I could, if I want to go to the halfway point, I can figure out the area of the triangle. I just have to know 1/2 base times height. You guys kind of with me? No, not at all. So if I have a probability distribution that's exactly a triangle, and this could happen, believe it or not. So the mean is still right in the middle there. It's symmetric and all that, but it's definitely not normal, right? If I want to know the probability from like 0 to 7, I just have to find the area of that triangle. Are you guys kind of with me? So that's beautiful. We see this all the time in mathematics. We have all these ways to do it algebraically and in the calculator and all this kind of stuff. But then there's a visual way to do it too that kicks ass. And the fact that probability is the same as area just tells me I've got to know the area, how to find the area in whatever situation I'm in. For what's called a uniform distribution, that's going to be this guy. Here's a uniform distribution. So I can have like 0 up to 4 maybe. Now real quick, what's the total area here? What's the total area got to be? 1, because it's the probability you have to add up to 1 or 100%. So considering that the total area here has to be 1, how tall can this thing be? A quarter, right? Because then wouldn't the area be 1? You with me? Little tiny bit? All right, little tiny bit, Jeff. So if I want to know in this situation, what's the probability 1 to 2? So from 1 to 2, how would I get that probability? How would I get this probability here? Just find the area. There you go. Cool. Maybe. If you can visualize a probability distribution, if you can draw it, and I keep drawing a normal curve because that's where we're going, but if you can draw the probability distribution, I just have to find the area that matches my question. So what is the probability I get from 1 to 2 for this given situation? It would be, this is 1 times the height, it would be 1/4 chance. So there will be like 4 problems in the homework that looks like this. Let that be freaking easy, right? It's finding areas of rectangles. What's hard about this stuff is really buying into what I keep trying to tell you, that the area is the same as the probability. But I'm hoping to God by doing this, it helps you make that connection. Now what sucks about chapter 6 is what shape am I dealing with in chapter 6, really? This shape. Do you know how to calculate the area of that shape? Some of you might. Anybody taking calculus? If you've taken calculus, you might know. To tell you honestly, the function that defines this shape, let me show it to you. Only look at this thing once, maybe. Yeah. So on the very first page of the section, here. All right, you ready? That equation gives you this shape. Some of you guys might actually even try to put this in your graphic calculator and graph it. That would be awesome. You pick a value for mu and you pick a value for standard deviation, you'll end up with a nice normal curve. It's really neat. Some of you guys are desperately trying not to think about that much. I don't blame you too much. But that's the actual equation that gives me that shape. Calculus is all about finding areas under curves. So that's why calculus could help me do this problem. Do we all know calculus? Hell no, right? You don't know calculus. Some of you guys are like, I don't know it, and I don't need to know it, and that's fine. And I understand it. Some of you guys are like, I just need this to transfer, man. Just stop talking about calculus. So thank God, in chapter 6, it's the same idea. It's the exact same idea. If I want to know the probability from 1 to 2, if that's what that is, I just have to find that area. We need calculus to find that area. Jeff, what the hell? So thank God, bless you. Thank God they have a table set up for me that tells me the areas that I might need. It's basically what I call empirical rule on steroids. So somebody help me out. Let's see if we can buy into this table. Somebody remind me or try to work out, if I had a normal curve, here's my 0. What is this that I'm putting here? What are these?
Z-scores.
Z-scores, I love it. They're the number of standard deviations away. So can anybody tell me what that should be, what this area here should be? The number. What area is this? What area is in here? Empirical rule says how much within one standard deviation? 68%. So how much is outside? If 68% is inside, how much outside? 32. So how much is on that side?
16.
16. Are we all cool with that?
Yeah.
All right, if you say so, Jeff. What the hell? You guys, I mean, that's how you work with empirical rule. What sucks about empirical rule? Not everything falls exactly 1 or exactly 2 steps away. Some things fall 1.78 standard deviations away. Negative 0.29 standard deviations away. The empirical rule can't do shit for me then. So we need something a little bit beefier, something that gives me a lot more information. So here it is. If you don't have that insert, and I certainly don't, somewhere through the years it has been lost. You don't have the insert. In the very back of your book hopefully is not as worn as mine. It's been through a lot. On the very back of there should be the z-score, the positives and the negatives. If some of you guys are actually looking at it, I love it. Cool. So let's see how the hell to read this thing. Just learning how to read a map. So what this does for me, besides give me a headache, why won't you focus? Okay, stay focused. Okay. The reason they set it up like this, now let's figure out what the hell. If I wanted a z-score of 1.93, negative 1.93, because I'm on the negatives. Negative 1.93.
Oh, that's cool.
Do you guys see that? So instead of having some long-ass list where you have to like roll it out of your book or something, they said, no, let's just make it into like a matrix so you can find. Now, I can only go out to 2 decimal places. If I wanted 3, then this would obviously have to be some kind of a fold-out pop-up book or something, right? So screw that. Let's just stick with 2 decimal places, that's fine. But for this problem, what do I want? I want to know the area. It always tells me the area below. This is key. Anytime I slow down, you know that must be key, because I normally talk really fast. This always tells me the area below the z-score that I look up. Always. That's the only thing this thing can do. So if I want the area above the z-score I look up, I have to do something else to this number. So what number am I going to look up to kind of check this? What z-score do I want the area below? Negative 1, 0.00, right? So let's look up negative 1, 0.00. What do I get? Which rounds off to like 16%. Why did I put 0.0016, by the way? Nobody yelled at me.
You were talking.
I know, I understand. It says 0.16. So you guys kind of see this? I mean, it has empirical rule in it, but it's so much better. So how the hell does this help us out in everyday life, Jeff? Well, all right, not quite everyday life. You got to give me a little break on that. But let's say you've got a problem where let's say that the average time it takes you to get to school is 17.3 minutes. You're a real, stats geek. I love it. And you're just analyzing your trips and you're just keeping track of it. So the average time is 17.3 minutes. And the standard deviation you figured out is, what is it, Jeff? I don't know. Let's say 3.092 minutes. You guys with me so far? And let's say that we further know that this is normally distributed. Everything in Chapter 6 really depends on it being normal. You with me? Because if it's not normal, I cannot use this chart. Let me say that again. This is empirical rule on steroids. Empirical rule requires a normal curve. So does this. I can only use this when it's normal. So a big part of statistics after this is going to be continuously, okay, how do I know when this is normal? How do I know when this is normal? I need some tests. I need some rules to know when it's normal. Why is that important? Because I got all the freaking answers if I know it's normal. But don't know it's normal, I can't do this. That would actually be stats 2, which we don't offer here. Okay, cool. So far so good. I got the mean, standard deviation. I know it's normally distributed, so I can even draw this thing out. Where would the mean go? Right in the middle. And let's say I want to know how often could I expect to get to class, to get to school in 12 minutes or less. What's probably at this 12 minutes or less. So you got to trust me on this. Some of you guys are not going to do this because you're like, that's just going to add time to my homework, Jeff. Leave me alone. If you do not draw this picture, you will be one of the people that are most likely to make mistakes. I'm not requiring you to draw this picture. I'm highly suggesting that you draw this picture. Right? Now, for some reason, people will draw this picture, and they put 12 here. I'm not sure why. This is a normal scale. This is a regular number line. Where should 12 go? Here. So, if you do that, I can't help you that much. The picture should help you if you put things in the right place. So I'm just going to put 12 down there somewhere. Doesn't have to be perfect. I just know that it's below the average. And if I want to know probably 12 minutes or less, can you shade in the area that represents? That's not too bad, right? It would be from this down. So I want that area. So it kind of makes sense that it's not going to probably be a very big answer here, is it? Because if it normally takes me 17.3 minutes, it's not going to be very often I get there in 12 minutes. I hit every green light, no cars in the way at all. And then I get there and I'm like, oh shit, that's right, it's a holiday. That explains it. So what is it, though, about this that doesn't immediately help me out with where I am right now? What do I need to be able to use this? Z-scores. I can only use this when I have Z-scores. I currently have what's called a raw score. It hasn't been worked yet. It hasn't been standardized yet. It hasn't been made into a Z-score yet. So it kind of makes sense. The first step here is to make a Z-score, and then the next step is look it up. And the final step is, does that answer your question? So take a minute and make that into a Z-score. Don't say it out loud. I know we're in a new context, but it's the old thing. Z-score formula is the same as always. Okay, so what do you get for the Z-score?
1.71. Yeah.
I love it. So you round that to 2 places, obviously, because this guy only can go out to 2 places, right? So to find this area then, now here's the further suggestion. Underneath here, I would put the Z-score in parentheses, just to keep me straight. Because there could be times when I have multiple variables, multiple values up here. So this Z-score is the one we just found. What Z-score is the mean? 0, because it's 0 away from itself. How do you get this area now? What have I got now that I could use?
Look on the chart.
Look on the chart. Look up negative 1.71 on the chart. It's programmed to tell me what's below it, so it's going to be the actual answer I want. So if you look up negative 1.71, you with me? 0.0436. You guys see that? So I get 0.0436. And I know that's my answer because that's exactly the question. I wanted below that. The chart tells me below. Sweet. I got nothing else to do. It told me exactly what I want. So there's a just above a 4% chance that I'll make it to school in 12 minutes. So if I got class in 12 minutes, there's a very small chance I'll make it on time. You with me? Okay. Stop looking at your watch. I don't have a watch. Okay. Let's continue with the same idea here. Part B. You guys try this one on your own. What's the probability that it'll take me more than 25 minutes? Try that out. Draw the picture. Put the mean on there. Put the x value on there. Do all these steps. Call me over if you need some help. If you don't have your z-score chart, that means you don't have your book. What the hell? Okay, so for the z-score, it's always my data value minus the mean. So for some of you guys, you got to be careful because I saw you don't always make this positive. You do yours minus the mean. If it's below the mean, it should come out negative. And now you see why it's really important you get the right sign on that z-score. Divided by the standard deviation. And what do you get there? 2.49?
Yeah.
Okay. Cloud sourcing the word. I like it. So, to get this probability now, I purposely gave you one that's a little bit different than the two we've seen so far. When you look up 2.49, what do you get? 2.49 is way at the end. You get 0.9936. Is that cool? Where is that on the picture, though?
It's everything to the left.
That's all this stuff. So 0.9936 thing. So then my probability, my answer is going to have to be what? 1 minus that, because it's the rest. So 1 minus 0.9936 is
0.0064.
Cool. So a less than 1% chance that I'll make it there in over 25 minutes. Yeah.
Why use the term minus? Why is 0.9
I like it. if the question would have been less than 25 minutes, it would have been this area, which is 0.9936. Because don't forget, what does the chart always tell me? The area below. And secondly, we've drawn the picture correctly. I expect this area to be small. So if you say the answer is 0.9936, that doesn't make sense. Right? It's another little check. I know it's going to be small. I've drawn this right. I put things in the right place. It should be small. That can't be right. So just take a step out of the math for a minute and just say, that didn't look right. I did something wrong. Just forgot to do 1 minus to get the other side. Now, real quick, because this is symmetric, I'm going to say this maybe once. If you get it, cool. If you don't quite get it, never, ever do it. Because you'll do it at the wrong time in the wrong way or something. Look up negative 2.49 for me. Right, that's just, we got positive 249 for the z-score, right? Look up negative 2.49.
Yeah.
I get the answer we got. Because of symmetry. How much area is in here is exactly the same as the area that's in there. Because of the symmetry, I can do that. If you get that, kick ass. It'll save you like 6 seconds.
Awesome.
I know, it's awesome. But you multiply that out by the number of times you're going to do this kind of problem, hey, it comes up pretty good. But if you don't get it, don't do it. Because people always kind of do it at the wrong time. Or they do that and they do 1 minus. And you're like, you passed yourself. Shit. You kind of with me? Symmetry makes a shortcut there. It's cool. So, let me give you one more situation. Then I'll give you guys some other things to try out here. Oh, using that same situation there, what was it? 17.3 and 3.092. So last situation here for these numbers. What's the probability that I would get there in between, what, Jeff? You can do it. 11 minutes and 16 minutes. What's probably take me in between 11 and 16 minutes to get to the college? Just try to attack this. Just try to draw it out. How many z-scores will you need? 2, because you got 2 data values. I like it.